Hey everyone, welcome back to physics. This will be lecture 9 of the course. And in this section, we're going to take a look at another kind of motion that we can model in 2 and 3 dimensions, and that is circular motion. So let's go ahead and jump into it. And we'll call this section 2.3 circular motion. Now, we can all imagine that when a particle moves along a curved path, the direction of the particle's velocity is going to be changing, right? So if I have some curved path like this, right, and I've got a particle moving along that curved path, I know that the velocity will be something like this at any given moment. And because the path is curving, I know that the direction of its velocity is changing, right? And so that means, what that means is that the particle must have a component of acceleration that is perpendicular to its velocity, which means that there's going to be an acceleration vector at a right angle to that velocity. Okay, so in this section, we're going to be specifically focused on this kind of scenario where the motion is circular. And we'll kind of start out by looking at what we call uniform circular motion, which is circular motion where the particle has a constant speed. So uniform circular motion is when a particle, basically you can say that it's when a particle moves in a circular path with constant speed. Now, speed being the key here, obviously the velocity can't be constant because the path is curved, so the velocity direction is always changing, but the speed, the magnitude of the velocity, is always the same. Okay, so I mean, this kind of scenario occurs like all the time. It happens a lot in nature. A couple of simple examples of what you might, where this kind of modeling would be applicable would be like a car rounding a curve with constant radius at a constant speed. Okay, so like if you're, you got some kind of a corner here, and you got a car driving along, right? And the car is just going to go around that corner at a constant speed, right? So that's an example of circular motion. And if the car's speed truly is constant or near constant, then you can model it as uniform circular motion. Another example would be like a satellite in a circular orbit. Okay, or another example would be like an ice skater skating in a circle. A circular pattern with constant speed. All right, so anytime you have an object moving in a circular path with a constant speed, right? So here's just a few examples of where that might be applicable in real life. Now, we just finished talking in the last lecture. We talked about projectile motion. Now, it's kind of important to think about how different these two types of motion are. Now, obviously, they don't look the same, but they do have some things in common. So in projectile motion, PM, and in circular motion, uniform circular motion, the acceleration is constant. Right, so in projectile motion, the acceleration was due to gravity. Now, in circular motion, the acceleration is constant, but it's going to be a different kind of acceleration than what we saw in the previous example. In our examples that we'll see for circular motion, the acceleration, the the magnitude of the acceleration will be constant, but the direction of the acceleration will vary. So for projectile motion, we would say that the magnitude of the acceleration and the acceleration itself were constant. But in circular motion, the magnitude of the acceleration is constant, but the acceleration vector itself is changing, specifically the direction. Okay, so our goal then for this, for what we're about to do then, is going to be to derive an expression for these acceleration vectors. So we want to derive an expression for, we'll say, average acceleration and acceleration generally. Okay, the instantaneous acceleration. Okay, so let's go ahead and do this. It's going to be a little bit of a lengthy derivation, not too lengthy. It'll be a bit of a derivation, so you'll have to probably pause the video, make sure things make sense, take your time on this section. But we will come out the other end. So what we want to do is we want to think about a particle moving along a path. Okay, and so we're going to say the particle is at P1, 1 instant, and then later the particle is going to be located at P2. Okay, now this is going to be a circular path, and so there's going to be a hypothetical sort of center to this circle, which we'll denote as O. Okay, this may not be a perfect drawing, but you can imagine. So the particle will move from P1 to P2 over the time interval AT, or delta t. So the particle goes from P1 to P2 over the interval delta t. Okay, so delta t. Now at P1 and P2, we will have two accelerations. We'll have A1 and A2. And now those accelerations are going to be perpendicular to the respective velocity vectors. So let's kind of draw in what those velocity vectors would look like. We'll call that V1. And then this one will be like slightly different direction, right? V2. Right? Remember, the velocity vector is always going to be tangent to the path at any particular point, right? So it's going to be in the direction that the particle is moving at instantaneously at that point. And then the acceleration vector, because this is uniform circular motion, meaning the magnitude of the velocity is not changing, the speed of the particle is not increasing or decreasing, it's constant. So there is no tangential acceleration, there is just radial acceleration. And so the way we kind of think about that is you've got these radial lines going to the center of the circle, and the acceleration is going to be along those radial lines. Right, and the key thing to notice here is that the magnitude of these acceleration vectors are the same, but they are in different directions, and they are going to be perpendicular to the velocity vectors. So we'll call this A1, and that one we'll call A2. Okay. Okay, very good, right? So this is hopefully pretty straightforward, right? This is just kind of the situation we've already seen about, we saw something similar to this with our projectile motion, even how the acceleration is perpendicular to the velocity in these cases, etc. So let's next talk about the displacement, right? So displacement is really, you can think of it as like this piece here, right? There's a vector here, and we'll label that delta S. Okay, so the displacement vector. So delta S is the displacement vector for the particle moving from P1 to P2. Okay, and the angle between these radial lines we're going to label delta theta. So we'll call this delta theta. That's that angle there. Okay. Okay, and then let's put a label on these radial lines. So how big is the radius of this circle, right? So you've got this circle, presumably goes all the way around here. What's the radius here? We're going to call it r. Okay, so that's the length of that radial line. Okay. All right, now let's, so we've got this picture, right? We've got this kind of picture of what's happening. We've labeled some quantities and some vectors and such. Now, let's consider the change in the direction of the velocity vectors, right? Because the acceleration here is all about changing the direction of the velocity. Remember, there's no tangential acceleration. There is just acceleration perpendicular to velocity. So the acceleration is 100% concerned with just changing the direction of the velocity. So let's look at that change in velocity. All right, so I'm going to draw another triangle here. And so this will be our v1, right? And that's really just this vector here. And then we're also going to have a v2, right? And these aren't to scale or anything, so don't worry about that. But basically all I'm doing here is I've got this vector here, v1, and I got this vector here, v2, and I'm just going to drag v2 over and connect it to v1. You get something like this, right? And then the change in the velocity, or the change in the direction of the velocity, we'll label here as delta v. Okay. And so basically this picture, again, is just drawn from the above picture. The picture above this picture just comes from this guy up here. And all we've really done is just join the initial points of v1 and v2. Okay. And I'm going to label this triangle too, because we'll be referencing it a lot. So we'll call him triangle 2. Now notice here, now this is sort of where you got to get your geometry hat on a little bit here. Notice that delta theta, right? Delta theta in this picture is going to also be found here. Okay, delta phi, I guess, is more of a phi than a theta. Okay, so that angle has to be the same, right? And why is this? Well, I mean, basically it's because, so delta theta is the same in both pictures, right? And we would say that's because a couple things. So first of all, v1, vector v1, is perpendicular to op1, right? So here's v1 and here's op1, right? So that's perpendicular. And also v2 is perpendicular to op2, right? So that's clear, v2 and op2. Right, and so these two together imply that triangle, the implication here is that triangle number 2 is similar to this guy up here, to op1, p2. Okay, so basically this triangle here and this triangle here are similar triangles. Okay, right, and again, just kind of take a little bit of time and make sure that you understand that. Maybe draw the picture slightly differently, bring the vectors all into the same picture. Maybe try to do a little bit more to scale, but it's kind of basic geometry can convince you of this. Okay, and so given the fact, we can say something like triangles that are similar triangles, that we can pull out some symmetries here, right? So the first thing we can say here is that the magnitude of delta v, the change in the velocity vector, divided by v1, so the magnitude of this divided by this is a vector, we'll say, that's going to be the same as the corresponding ratio from the triangle up above, namely delta s over whatever the radius is. Okay. Right, so that's just similar triangles, right? That's just the way that works. And so a little bit of algebra there can get us to this. The magnitude of the change in velocity vector would be equal to v1 times delta S divided by R. Okay, right? So this is going to be important, this piece here. Now, we know from just first principles of physics, right? That's some of the stuff we talked about earlier. I'll just write from first principles. We know that the average acceleration is equal to the magnitude of the change in velocity divided by however long it takes for that to happen, the change in time, delta t. Okay, and so the implication here is that, right, we have another expression for delta v right here. So the average velocity should be equal to the magnitude of the change of velocity divided by delta t, which we can sub in this quantity for this numerator. So we get v1 delta s over r, all divided by delta t. And we can do a little bit of rearranging there, and we get v1 over r times delta s over delta t. Okay. All right, so let's go ahead and switch pages here. I'll rewrite that. So we have that the average acceleration is equal to delta s over delta t times v1 over r. Okay, so the magnitude of the instantaneous acceleration at point P must be the limit expression of the above as we take P2 and make it closer and closer to point 1. Namely, we shrink down the time. Right? So acceleration, the magnitude of the acceleration would be equal to the limit as delta t goes to 0 of this expression. I'll write it like this, v1 over r, delta s over delta t. And of course, v1 and r can come outside of the limit. And we have delta s over delta t. Because as delta t goes to 0, obviously the displacement is going to also change, right? And so notice that delta s over delta t is just the change in position over the interval delta t. So it's really just v1 at point P. P1 can be any point of the path. So we can really kind of drop the subscripts, can't we? Because the change in position is just, over time, it's just a velocity, right? So note delta s over delta t is just the change in position over the interval delta t. I'll just write it like this. It's just the change in position over the change in time. And this is just v1, isn't it? Right? Or, well, let's just leave the subscript off. So it's just v, right? That's just the velocity. Right? And we don't, the point is that we can, the velocity can be anywhere in the circle, you know, so the subscripts can be ditched. So a is really just v1 over r times the limit as delta t goes to 0 of this ratio delta s to delta t, which is just, again, dropping the subscript v over r, and instead of, and what happens when this limit is taken? Well, it's just velocity, right, like so. And so this is ultimately just v squared over r. Okay, so this is the instantaneous acceleration magnitude for uniform circular motion. So this would be, another way to write this would be a, the radial acceleration, is equal to v squared over r. Right, the subscript r here, or sorry, rad, is to indicate that the acceleration is all directed along the radial lines of motion. Okay, all of the acceleration is along the radial lines. So a rad means that all of the acceleration is along the radial line of motion. Right, which is what we said at the onset. If you remember the picture we drew, right? This is the radial line here. we said all of the acceleration is there. And the reason we know that is because the magnitude of the velocity is constant, right? So namely, the speed of the object is unchanging as it goes around, right? The only thing that's changing is the direction of the velocity, not the magnitude. So this arad here is frequently referred to as centripetal acceleration. So because all of the acceleration is along the radial line, right? It's directed, namely directed towards the center. Of the circle. This is sometimes called centripetal acceleration. It's sometimes called centripetal acceleration. Okay, so you've certainly heard that term, I would say. Most people have heard that term. Okay. All right, very good, very good. All right, so that's how we can quantify the acceleration of an object under uniform circular motion. Now we can also express the magnitude of the acceleration in terms of the period. Okay, so another expression that will be frequently used with this kind of stuff has to do with expressing the acceleration, the magnitude of the acceleration in terms of the period. So we can also express the magnitude of the acceleration in terms of the period. Now, what do we mean by the period? Right, the period is the time, and it's usually denoted with a capital T, the time t that the particle takes for one revolution. Okay, so the magnitude of the acceleration can be expressed in terms of the period. And so how do we do that? Well, so in time t, the particle is going to travel one revolution around the circle. So in time t, the particle will complete one revolution. Now, what is a revolution? So that's 2 pi r, isn't it? The distance is equal to 2 times pi times whatever the radius happens to be, right? And so we would say that the velocity is equal to the distance over the time, and so it's equal to 2 pi r over the time it takes to do a revolution, which we just said is t. That's the period. Okay, and so when we plug all of this into our expression, the previous expression, one sec, let me flip over here. So we can plug all of this into our arad equals v squared over r expression, right? And we get, what do we get? Well, we see that arad is equal to v squared over r. That's what we just showed. And we know that v is equal to distance over time, 2 pi r over t. So we can put 2 pi r over t. We got to square all that and divide it by r. Right, and when you do all of the squaring and the reduction and the cancellations, what you end up with is 4 pi squared r over t squared. Right, so maybe you're told how long it takes to do a revolution, and you know the size of the circle. Well, you could figure out the radial acceleration then from that information, right, without explicitly knowing what the velocity is. Okay, all right, very good. So those are the two kind of main things we want to get to in circular motion. We'll obviously come back to this in later sections, but let's do an example quick. Let's do an example. So carnival ride example. So in a carnival ride, passengers travel at constant speed. Travel at constant speed in a circle of radius 5 meters. Okay. Right. So there, so you've got some kind of a spinny ride, and the radius of the spin, or the radius of the circle, is 5 meters. So you get in this thing and you're just spinning around this circle of radius 5 meters, and it says constant speed, which is the case with many carnival rides. If you get on like a tilt-a-whirl or like some kind of a sky swing or something, this is usually the case. It's constant speed. It speeds up initially at the onset, but then once it's in motion, once it's going, it's more or less constant. Okay. And so passengers will make a complete circle in 4 seconds. 4 seconds. They complete a circle in 4 seconds. What's their acceleration? Okay. All right, so what is their acceleration? Right, so we can imagine this as a uniform circular motion kind of problem. Right, so I've got 5 meters is my radius. Right, I'm this person on this thing here. My velocity is looking like that. My acceleration is perpendicular. Okay, and the question is just, what is that acceleration? What's the magnitude of that acceleration? And so that's just our A radial, our A rad. We know it's v squared over r, and further, given the information that we have, namely the period and the radius, we can use the second expression that we derived up here. So it's 4 pi squared r over t squared. And just plug in all these quantities. 4 pi squared, and the radius is 5 meters. And the time, the period, is 4 seconds. Okay, so it looks like this. And so when we do all of these calculations, you'll notice that we'll get meters per second squared, so that's acceleration, sounds good. And when you do the calculations, you'll see that you get 12 meters per second squared. So the acceleration is 12 meters per second squared, which is pretty fast, actually. That's why the ride is thrilling, right? The acceleration, even though you're not really speeding up, what makes the ride thrilling is that radial acceleration of 12 meters per second. So you're being kind of pushed, in a certain direction at 12 meters per second squared. That's why the ride is kind of thrilling and enjoyable. So that's the way to sort of get to this quickly, but let's actually take the less direct way, right? Let's start with calculating the velocity. So the velocity is going to be, in this expression, would be 2 pi r over t, right? So it's just the distance traveled divided by the time it takes to travel the distance. So 2 pi times 5 meters over 4 seconds. So the magnitude of our velocity is 7.9 meters per second. Right, and therefore the A rad would be v squared over r, so that's 7.9 meters per second squared divided by 5 meters. Right, and so you'll have meters squared, seconds squared up top, and a meters down below, so that'll all cancel, and when you do the math, you do indeed get 12 meters per second squared, again, as you should, right? Okay, perfect. So that is an example of how to, use uniform circular motion in kind of a real world example. Now, we're not going to get into this a lot, but we'll just mention what circular motion is like in the case when it's non-uniform, right? So if the speed of the motion varies, then some amount of the acceleration must lie parallel to the velocity vector. And in this case, what we would call that non-uniform circular motion. So this can be somewhat more complicated, so we're not gonna. So non-uniform circular motion. So basically the gist of non-uniform circular motion is just that the speed of the object varies. Right, and the implication of that is that some portion of the acceleration must be parallel to the velocity vector. So some portion of the acceleration is parallel to the acceleration, to the velocity vector. Right, so that's, I mean, we've seen this in previous lectures, how, you know, the acceleration can be broken down into tangential and perpendicular components. And so that's what's happening here. So an example where this model could be applied is in the case of like a roller coaster, right? If you think about a roller coaster, it kind of moves up and down, right? Maybe it has something like this. Maybe this is what the roller coaster looks like. So for certain sections here, you could apply non-uniform circular motion to describe the changes in velocity and acceleration, right? So you could specifically do it when we're rounding hills and valleys, right? So in this kind of motion, A radial is still the same. In this kind of motion, A rad is still equal to v squared over r, but there's an additional component of acceleration that's not captured in this expression, and we call it, so, but there is an additional kind of acceleration called, we'll call it a tan, right? A tangential acceleration that is going to be this portion, this component of the acceleration is going to lie parallel to the velocity vector, right? So a total velocity, total acceleration vector is going to be equal to this a perp plus a parallel. And so in circular motion, we tend to change the names of these things and say that acceleration is equal to a rad. That's kind of the radial acceleration, which is analogous to this perpendicular acceleration, and a tan, which is analogous to this a parallel, right? So at each point, like for example right here, you're going to have a radial acceleration like this, but because we're going downhill, there's also going to be some component of acceleration headed in this direction, and so combined you'll have an acceleration kind of in between, won't you? Right, and same thing up here. You'll have acceleration towards the center of the arc, but you'll also have acceleration because we're going uphill in the reverse direction, and so your acceleration will be something intermediate. Okay. So it turns out, and we won't derive this, but a radial we saw is v squared over r. A tangential is going to be equal to the derivative of the magnitude of velocity, right, with respect to time. Okay, so this is very intuitive, right? Some of these are somewhat more challenging to model just because you have these different pieces of the acceleration puzzle. But all right, we'll get into more of this at a later date, but this is just an introduction to the idea of non-uniform circular motion. Really, the radial acceleration stays the same, but you have this additional component of tangential acceleration. All right, I think we will leave it there, and we'll see you all next time. Take care.